This is a presentation for the 2023 meeting of the Society for Mathematical Psychology. Most of the work was done by Jan Brandzæg, and he will be presenting that at the live conference in person. Our topic is prior expectations. Lifelong experience with faces being convex gives most people the impression that this hollow mask is actually a convex face. So how do you describe and model the power of these expectations? And really the only way is to assume that you can describe this as a probability distribution over suitable parameters. That here you have some parameter, you then can say it's this likely that the parameter has this value, this likely has this value, and so on. Then your prior belief might be, for example, this distribution. Then you get some observation, so sensory data, that is your likelihood. You can combine these by multiplying the two. That gives you an updated belief that will be your perception or your posterior, as for example in this figure from Harker et al. You can then put that into equations, and in this case, because we have Gaussian distributions, you multiply those, that gives another Gaussian. So you can instead provide equations that describe the mean and the precision, where precision is inverse variance of the new distribution. And so the mean is, again, precision weighted. So for example, if this distribution here, the likelihood is twice as precise as the prior, then the mean of the posterior will be in a ratio of 2 to 1, closer to the more precise distribution. And the precision of the new distribution is the sum of the precisions of the two that have contributed to it. We find the same equation in slightly different form in Petzler and Glasauer, also here in Bogardi, and some other papers. And the idea quite often is that here the likelihood changes a prior belief into posterior belief, and that then becomes a new prior or prediction for future observations. So let's see how that works. I start off here with a completely flat prior. So then the first posterior, this black stippled line, is right on top of our measurement, the observation. That then becomes the prior for the next observation. So that is the expectation. This is the actual observation. These then get combined into this perception. And because these have the same precision, that is right in the middle. Then here, another trial, another observation, and another. Here you can see more clearly that the posterior is precision weighted and closer to the more precise expectation here. And also that these keep gaining precision. So the posterior is always more precise, becomes a new prior, and so that just keeps gaining precision as shown here. You can also look at that in the equations. So the precision of the posterior will be the precision of the next prior, which will be the sum of these precisions. So here we had started off with precision 0. We added then the precision of the measurement, and that gives us a posterior and new prior that now has the same precision as the measurement. Then here in the next trial, we add again the precision of the measurement. So we end up with twice the precision of the measurement, 3 times, 4 times. So that just keeps happening. And when you look at the equation for the weight, what is the weight that the likelihood that the new observation has on the mean of that new posterior? And that weight just keeps decreasing independent of the process variance and even independent of the precision of the measurement. It just decreases hyperbolically if you only care about the relative weight. That seems a slightly odd property. And I thought maybe that's because this prior is intended to represent only the precision with which the mean is known, but not the expected distribution of future experience, which you would need, for example, for risk-sensitive decision-making or for change point detection. But there have been proposals of population codes that can represent probability distributions. And so I thought, well, maybe you can design an alternative prior in which you just average these distributions. So you just add them up and you keep renormalizing. So if we start again with a flat prior and this observation here, that average would look like this. We get a new observation, we average again, and keep doing that. Then we end up, for example, with this here after 5 observations. And that is summarized here. If you can just add up this sensory information, it's logically possible also to just add up the posteriors, which after all seem to be what you consciously experience. So what would that look like? Starting again with a flat prior, and second try looks the same, but now this prior here and this posterior get added up, get averaged to produce this new prior. Then this here gets added in, so we have added this up. Then we multiply that blue prior with that green new likelihood. That gives us here this slightly skewed posterior. This then gets added in again to give us this, and so on. Now, one thing about this is, if we change the order of these first 4 experiences, if we just reverse them, the end result here will be just the same as before, because after all, we just multiply distributions and multiplication is commutative. It doesn't matter in which order you do that. The same goes for addition. So we just add things and that ends up with the same distribution. But this averaging of the posterior, because we only get the posterior by multiplying, but then we have to add again, now it matters in which order we do things. So these no longer look the same if we just do things in a different order. That is also why we can give an equation for the precision or for the variance of this posterior here. We can also do that here. If we just add up the distributions, then in the long term, that resulting posterior and new prior will converge on having a variance that is a sum of the process plus twice the measurement. If instead you use the central tendency, instead of always adding in a distribution, then it would be the sum of the process variance and measurement variance, which would make a good prediction of future experiences. But for this here, we can't give an equation because the shape of the distribution and its variance does depend on the order in which observations are made. If for some reason we are stuck with using our conscious experience and putting that down in memory, well, that would be interesting. So we wanted to fit that to some actual data and took data from Petzschner and Glasauer, 2011, who had people navigate through a virtual environment in different sessions in which the average within the session was either small, intermediate, or large. And they expected, again, this Bayesian Q combination such that you create an expectation of where these stimuli are on average within a session. Then say you get given this distance here to traverse through the virtual environment. So that gives you your sensory data, your likelihood, but your actual conscious experience is this combination with a prior, so you only experience that posterior, and that posterior is what you try to reproduce, and therefore you will get regression to the mean. Here are the data from Petzschner and Glasauer's participants. Here are the data from one of their models. And we produced what we thought was their model and got this here because we used that multiplicative prior, which just keeps adding up the precision. So very quickly, the new observations have very little influence on your perception. That is why these lines are so flat. And then Örjan said, but hang on, that looks very different from this here, so we can't have done the same thing that Petzschner and Glasauer did, which really I should have noticed 2 years ago because I thought the results would look like this, and I should have noticed the difference with what they actually have produced here. So we looked through the paper again and found a set of equations that I had previously missed because I had focused on these, because I had previously read Maybach, which I treated as authoritative, and thought that Petzschner and Glasauer were doing the same thing as Maybach, and they're not. They have a separate set of equations which generate the next prior, and these equations they use only to generate the response. So what does the next prior look like under that set of equations, the equation 11? That then looks like this. And what happens is that the prior gains a little bit in precision over the measurement, but not a lot. That stabilizes very quickly, and therefore the new observations are not being ignored to the same extent. So when we did this as well as we could, we got something that at least looked pretty similar to Petzschner and Glasauer. It's not exactly identical because there were some details of their modeling that they didn't specify. But now we had something, we had a result that we could compare to the data, that way we could fit the models. And then we compare the way Petzschner and Glasauer did that. We compared that with the multiplicative prior like Maybach used. We compared that to the sensory distribution, which we've shown you, and also using only the central tendency, so either the mean, median, or mode, then the posterior distribution, which we've shown you, and again, posterior mean, median, or mode, and also a case of not having any regression to the mean at all. And the worst fit by far was a multiplicative prior, like Maybach used. The next worst was our posterior distribution. And when we then look at the weights, which say what is the probability that one particular model really is the best fitting model, it's basically very, very clearly what Petzschner and Glasauer did, and everything else is pretty much indistinguishable from zero. So these just don't fit, at least not the Petzschner and Glasauer data. Nevertheless, we can identify several papers, not quite the 11 we had counted when we wrote the abstract, but still because some of them don't have quite enough information, because both what Petzschner and Glasauer did and Maybach's prior, they both are iterative and take a posterior as a new prior. But when we look at the equations, we can identify some papers that actually use the same as Maybach. Then we have what Petzschner and Glasauer did, that fits the data. Then we have something that is not quite the same, but similar to our additive prior, where we just added the sensory data. And so we come to the conclusion that distinct kinds of prior exist. They are different enough that it really matters which you choose. And out of the 4 priors we have identified here, 3 have been used in the literature, but we haven't seen any explanation of the choices that people have made, why they use one prior rather than another.